All right, so welcome everyone. This is a teaser, a preview of the Concurrency Tools in the C++ standard library hands-on workshop. My name is Mateusz Pusz, and I will be providing you this short preview of how the actual workshop looks like and what we are going to learn. It's actually hard to fit in those 45 minutes that we have today, so I tried really hard to actually find something that will be closed enough to actually teach it at this point, and also easy enough to actually be able to maybe finish some simple exercise in the end. If you have time, we're actually going to do this exercise online, because typically we are doing lots of exercises and hands-on exercises and hands-on workshops on my trainings. But if not, you will just get a homework and we'll see how it works with timing. But first, let me introduce myself. I am so-called modern C++ evangelist. I like sharing my knowledge. I love sharing my knowledge. I love answering questions about C++ and discussing C++. So if you have any questions regarding C++, please reach me out during the conference or offline, and I will be happy to answer those, right? Also, don't be shy. Please ask questions. Please participate in the workshop. I promise I don't bite, and I love, as I said, discussing those things. I'm doing C++ for more than 20 years right now for fun and living. By fun, I mean doing open source project, MP-Unis library. Maybe you've heard about it. And also I worked at Intel for 13 years, EPAM Systems for 10 years, and I'm still consulting many code bases all around the world. I've been doing many different positions in many different companies, so I have broad experience with engineering. And I'm also a trainer for 15 years right now. So 15 years, it's a lot of time. I actually started before C+11 was shipped as a trainer, and I'm doing this ever since. Besides, I provide the coaching, mentoring. I'm a consultant for many corporations and a conference speaker. Besides that, I am an active voting member and contributor to the C++ committee and the standard. I'm also trying to be active in study group 14 and study group 20, so the education and low latency high performance group. I'm also a member of mutexes, and my main interests are code performance, low latency, safety, and maintainability of the code. The motto of my training is to master C++ with your fingertips and not just with your eyes, right? If you have never actually attended workshops are totally different than actually lectures. Doing actually preview in 45 minutes is quite hard, and it's quite hard to make it as interactive as a regular workshop, but we're going to try, right? If you're not going to type code, I believe you are not going to understand it and basically know it, right? My experience is that people understand code written on a slide, and then when I ask them to actually write something by themselves in a similar, even like 3 times easier, they don't know how to start, because they have no muscle memory that actually allows them to type it, right? So active practice is what makes knowledge truly stick, right? You have to build your muscle memory to actually type the code, and this hands-on experience is actually, I think it's crucial to actually workshops and to actually be able for you to apply the knowledge from day one when you actually come back to your work. And yes, my workshops and exercises are not easy. You will sweat a bit, but that's exactly what makes the knowledge last. If you have enough time, we are going to switch to Zoom breakout rooms and going to work on this interactively in the exercise that is by the end of the workshop, but we are tight on time, so maybe you will not have time for this. But if you have, we're going to do breakout rooms. Typically, we are doing this on the workshops, either online through Zoom or on-site. Of course, we are doing hands-on then. Breakout rooms are basically 3 to 5 person per room, isolated environment, when one person will share the IDE, which will be a compiler explorer link that I sent to you. And basically, you all discuss and solve the exercise together. You give the control to each other, you switch the roles, and please be active, discuss, share feedback with everyone. If you are stuck, you don't know how to proceed, or you got to get some feedback about the exercise, there is a button, ask for help, that you can press, and I will be there immediately to help you in the room. Anyway, I'll be switching between different rooms and providing feedback to you. If you're done, just leave the room, and I know that the group is done, and I can basically scope on the groups that are still working, which is easier to finish on time for all of the groups. The training I'm going to provide at this conference is actually a part of my longer 4-day training called Modern C++ Concurrent and Asynchronous Programming. At the conference, I will talk about concurrency in the C++ standard library, which is the first part of this training. Besides that, I'm going to talk about coroutines and senders receivers in the other parts of this training. Actually, after 45 minutes, I'm going to provide another teaser for the third part of this training. So you're going to have a teaser for the part 1 and part 2 if you stay longer and see both of them. You can check the full training offer at my website, but let's see what is in the training that will be provided in this conference later on. We are going to talk about all of the tools that are in standard library responsible for multi-threading. So you're going to talk about threads, mutexes. We are going to talk about logs, deadlocks. We provide some design patterns that help you actually with writing proper code. We are going to talk about old synchronization primitives like condition variable, call ones, but we also introduce the new ones that are much more powerful from C++20, semaphores, latches, barriers. We are going to talk about futures and package tasks, asyncs, promise, all of the things, and we discuss why actually it's not the best solution anymore to write actually code based on that. Unfortunately, if you do due to timing constraints in the training that we'll going during the exercise, we are not going to talk about atomic and memory model because it's like 2 additional hours and we don't have this time, right? As I said, my training is a 4-day training, so I have to cut it out, something usually fit in 1 day. So let's start. Why are we actually here? Because from like 2004 or 2006, the CPU cycle, CPU clocks do not rise anymore, right? You don't get the performance for free on one single core CPU. In order to have better performance, you have to start to work on more CPUs at a time, right? So you have to actually deal with concurrency, parallelism, asynchrony, and so on. And this is applicable everywhere, right? For every application in every domain nearly, and touches everyone on the market, every developer from finance through embedded. All right, so let's dig in. Before C++11, actually, there was no multi-threading support in C++ at all. It was huge undefined behavior. If you will look into hundreds of pages of the ISO standard, there will be no single word thread. It was just a huge undefined behavior, right? Basically, we had to deal with all specific implementations and provide non-portable code to make it happen. With C++11, we got core language support with thread-aware memory model and C++ standard library facilities to manage thread, protect shared data, synchronize operations between threads, and provide low-level atomic operations. Right? In C++11, we got a lot. We got thread, we got some namespace this thread that allows us to get the ID of the thread, sleep, or yield. We had different mutexes, different logs, providing array idiom for mutexes, so resource acquisition initiation for resource management. We have a log function, once flag, a call once, conditional variable, promise, a future, and async, right? And atomic operations, of course. So this was a huge change in the language. I assume that most of you actually are familiar with those because those are on the market for 15 years right now. So in this training, we are not scoping too much on that. We are going to briefly talk about them, but we are going to scope on the newer, better tools that we get. C++14 didn't extend much, 17 as well, but provided parallel and vectorized algorithms, which is nice. And C++20 was another huge change on how we deal with concurrency, right? And this is actually what we are going to scope a lot during this training. We are going to talk about JFrets, cancellation, and basically stop sources, counting semaphore, binary semaphore, latches, barriers, atomic references, and some additional operations. And of course, there are coroutines. But coroutines is a separate 1-day training, so we are not going to fit it during this workshop. Today, as a preview, as a teaser, we're going to talk about counting semaphore and the JFret. So you are going to see some part of those new tools, and possibly, hopefully, you will learn something even from this teaser. But first, before we actually do any code exercises with the multi-threading concurrency, we have to deal with one really important thing: debugging, right? Debugging by prints. When you're dealing with concurrent code, you typically see often broken console outputs. And you often want to actually use console outputs to see how threads progress. With C++20, we got a new tool called async stream. Async stream provides you an atomic operation for the streams. It means that it will concatenate this entire buffer on a side, and then basically atomically transfer this buffer to the underlying stream when basically it is done. All right. You can do this either in the scopes, so basically it will be transferred on the destructor here, or you can do it through a temporary object, which means that the destructor at the end of this line will trigger this emission of the buffer to the underlying stream. The interface of the stream typically is connected to so-called sync buffs or the buffers, and the buffers will have the API like emit, get wrapped, and set emit on sync, and the sync function. Emit basically is responsible for this atomic transfer of data from the higher level to the lower level stream, right? Sync means that the stream should be flashed. And then you have async stream, the one that you are dealing with. So async stream also have emit, get wrapped, and RDBuff to get the buffer from the previous slide. So how this works in practice? If you have async stream here out for cout, if you type hello to cout, nothing is flashed, nothing actually is present on the screen yet. Only when you do emit explicitly, the characters will be transferred from async stream to underlying buffer. So cout will have it, but will not print it yet because it was not flashed. Okay. Then you add more to the buffer, higher level buffer, and you say notice flash, right? Handle is different from new line with the fact that actually it triggers a flash on a stream. So it triggers the flash, but on the higher level stream, so nothing still gets printed. And only when you emit it, so you transfer this to underlying stream, this word is being attached to the current cout, and there's the flash, so this will be presented on the screen. Then you add greetings, still not present on the screen with a new line, and here it will emit, but still not flash. All right. This is basically how it works. If you write two async streams like this one, we have out1 with cout, and you write hello, then we can create another scope with async stream and say get wrapped. Get wrapped will return us whatever was wrapped here. So we are going to print on cout as well, and we write goodbye planet. Notice that at this point this object dies, because this is the end of this object, right? And also of the scope. So actually this is what's being transferred to the cout first. That's why you see this line first on the output. And only after that you print word to the outer async stream with a new line, and then close it, which will emit things to cout. That's why it's printed as a second line, right? So this is how you deal with async streams. This is how you want to write something that is thread safe for printing, which is really useful for any debugging of concurrent code. One last thing is maybe when you're actually writing your custom streaming operators for your classes, then you typically deal with not async stream or cout. You typically deal with something like ostream reference, right? This is what you get as an argument, and this is what you return from those streaming operators. In this case, you don't know if you are dealing with async stream or not. So how you can benefit from that at this point? The library provided you the manipulators called emit on flash, no emit on flash, or flash emit that actually will do all of those operations, assuming that the O stream is basically reference to the async stream. If it is, then it will work as expected. Otherwise, those will just be ignored and do nothing. All right? Good. So this is how you are doing the thread safe logging. So now we are having this this piece of code, right? We have some IO stream, sync stream, or thread headers, and we have hello function that prints something in atomic way. Actually, I don't have to use async stream here because it doesn't concatenate stuff, but still it's nice to actually present it here. And I have a thread that prints this function as a thread function, uses this function. What's the issue here? Who sees that? Anyone see an issue with this code?
Yes, so we are not joining the thread at all, as far as I see.
Good, exactly, right? So the thread is being spawned, but it never joined or detached. It means that there will be to terminate on a destruction of a joinable thread, right? This is the design of C++11 threads. You have to either join it or detach, otherwise you have a terminate, all right? Basically, the committee could not agree what should be the default at this point. Both of them were considered valid solutions. We couldn't find what is the better default, so we decided to just leave it for the user and provide a clear error that something is wrong in the logic of the program. Right? If you do not decide before the stud object is destroyed, terminate will be code. Today we know that join probably would be a better default, but it's too late. C++11 was shipped, and this is how it works. The act of calling join cleans up any storage associated with the now finished thread. Stud thread object is no longer associated with any thread. Such object is no longer joinable. Joinable will return false after joining, all right, because it's already joined. We can call join only once for a given thread, right? Otherwise, you will get basically joinable false, and it will be an issue. The second call will result in system error being thrown with invalid argument being a value of the system error. All right, so we are joining. But still there is some issue with this code. What may be an issue here?
What if hello throws?
What if hello throws? Exactly, or do something may throw, right? Do something may also throw. Exactly, this is the issue, right? So actually, this is not the code that you should write. You should write the code like that always when dealing with C++11 threads, right? Because even if do something today does not throw, then it doesn't mean it will not throw tomorrow or the day after or in a month, right? You should always assume that every single line of your code may throw an exception, and this is good, right? You just should write a code in such a way that it is aware of possible early returns, because exception actually, if you think about it, is just yet another early return from your function, right? So this is how you should always write your code, which is cumbersome, right? And of course, there's an issue if the hello by itself will throw. This is what actually was mentioned before. But well, we are not going to deal with that here. But it's also a possible issue to handle that, right? The interfaces like future and promise handle that and transfer the exception pointer from the thread function to the outer receiver, and to actually propagate the error. In this case, nothing will actually we will have a problem, right? But we're not going to talk about exceptions here. I just want to make sure that you know how to deal with the thread itself, not the thread function here. All right. Also, another possibility is to detach. If you don't want or don't need to wait for the thread to finish, you can detach that. Typically, it's not a good idea in the production. Typically, you should have something like a thread pool or something similar, but we often detach anyway, right? Detaching breaks the association with the thread, and the thread object no longer basically refers to it. So you cannot check if it's joinable or whatever, because it's basically gone, right? It's like empty object after that. But terminate will not be code. Where we are using detaching, right? We typically use them for so-called daemon threads. Typically, those are typically long-running tasks that run for almost entire lifetime of the application and perform a background task. Those are also fire and forget tasks that you can spawn. If you will actually attend the other workshop about the structured concurrency, we are going to talk how actually you can deal with detached work in an efficient way through async scopes, for example. But this is different training, not this one. Okay, so we have start task function, and we create some thread which does something, and we detach. What is an issue here?
T is destroyed at the end of the scope?
T is destroyed. In this case, T destroying is fine because, as I said, after you detach, actually it doesn't refer to anything, so it's fine to destroy T.
The problem
another
is
issue.
capturing by reference in the lambda, and I variable would be destroyed when we are moving out.
Exactly, right? So this is potentially long-running task, right? It has plenty of iterations, right? So it is possible that you actually will spawn this thread, or even just schedule the spawning of this thread, detach, and go out of this function, and all of this work will refer to the local storage of the or the local variable in the function that's already gone, right? So this is reference to dangling reference of the function. That's wrong, right? You should make thread functions self-contained and copy the data into the thread rather than share it in general, right? It's a bad idea to create a thread within a function that has access to the local variables in that function unless the thread is guaranteed to finish before the function exits, right? So if you are joining in a function, then everything is fine. But if you're not joining, you're detaching or just returning a thread, for example, some value or whatever or result value from the function, then it is an issue. All right, let's move on to C++20 abstraction that actually tries to fix it. At least the joining problem, right? We have JThread in C++20. JThread, as the name suggests, it's a thread that joins by default, right? It joins on a destruction. It can be additionally cancelled and stopped in certain situations, which is also different than the regular thread, because regular thread does not have this feature. During this teaser, we are not having time to actually talk about cancellation, but we are going to talk about cancellation in the full workshop after the conference. All right, so JThread. This code is exactly the same code as this code on the right-hand side. This should immediately tell you that you should prefer this one and you should forget about this one. If you have C++20 in your project, there is no good use case for thread anymore. Please don't use it. You can detach JThread as well if needed. And then of course, it will not join, right? But if you are in C++20, just refactor all threads to JThreads and you are going to be in a better length right away. And of course, if you have explicit joins in your code, it's not a problem. You can leave them or you can remove them later on. But if you have them explicit, it's nothing wrong about it. Right? Because JThread, if it's already joined, will not join again. All right. So we have this thread function that takes integer I and a string s. And you have a local buffer. And we put some data into the buffer, and then we create a thread function that we pass the free here as an int and then buffer as a string. And then we detach. What might be an issue here? Anyone? Notice that this time we are passing by value, right? So there's no reference capture. So it seems we are doing everything correct, but there is an issue still. Who sees the issue? The issue is that the sum params is actually not a string, right? Is it the array of characters with basically during the template call, because the template call will convert to a const star, right? So the pointer to characters. Which means that the JThread will sorry, not some buffer here, right? This buffer will be the const star, and this means that the JThread will internally store const star pointer and then detach. And then at some point, this function will be spawned, and it will use this const star pointer and will try to convert it to string at this point only. Right? So it looks like you're having capturing by value, but you're capturing const star rather than the string itself. Okay, because this is template. Template will not know that you want to have a string. Template will just take the type of the argument you pass and store it the same as lambda stores it, right? So it will store by value, elements by value, so the pointer will be copied, or references by references, right? So by value will be copied by calling const star. Those are different types, so it's dangling again, right? In order to pass an argument to the thread function, it is first has to be provided to thread constructor. By default, arguments are copied into the internal storage, passed to the thread function as values. Values means as a temporary or moved, right? If argument parameter conversion is needed, then the thread for a thread function, it happens only when the function is being called rather than when you create a constructor. Call the constructor to create the thread or JThread object, right? Copy is done. This copy is done even if the thread function is expecting a reference. The thread function signature does not make any difference here. If you pass by value, it will just be copied. So the recommendation is to explicitly create a temporary of the thread function parameter types directly in this toThread constructor in case argument parameter conversion is needed. So you have to write string of buffer and then you are fine. Because then the conversion will happen on the call side and you will store a string inside of the JThread, and then when function is being called, it will just pass this string into the thread. As we said, it will be moved there, right? So it will be no performance overhead, there will be no additional copy. All right, so with that, what is an issue here? Who sees that?
Seems like something similar to the one several cases ago with dynamic reference capturing. So this time threadfunc expects reference to int.
Actually, there's no dangling here. The problem is that the dangling there's no, because you are just passing int into the JThread internal storage, and then potentially this reference will just refer to the internal storage of JThread. So it should be fine. There's another issue. I just told you the rules about it on the previous exercise, but
yes.
It requires to understand what actually is written here or here. And I'm talking about this on my advanced model C++ classes when you're talking about language, right? What does it mean that they're passed as values? So this int will be passed as an value to the thread function. This int. So what will happen here? Can value bind to an value reference? No, you'll get a compile time error at this point, right? If it was const value, then it will bind correctly, right? But as it is a regular value reference, so this code will not compile. Okay. But sometimes you really want to pass something as a reference to your thread and not make it dangling, right? So how you should deal with that with such interface? For that, you can use reference wrapper, right? You can use reference wrapper to pass arguments to any actually any template, not only thread, right? And this will basically work as a reference capture for you. So basically what it means, the reference wrapper just behaves as a reference and it can be copied or assigned. So basically it stores a pointer inside. And you have two factorial functions for it. You have ref and cref. Ref creates reference wrapper of t, cref creates reference wrapper of const t. All right, so here you could write something like int studref some params, and then you're passing this by reference, and this may update this if needed or share between different threads, right? In this case, it is safe because this is JThread. It will join before calling, stopping this function, so int will not go out of scope. It will never be dangling. All right, unless you do detach here or return the thread. But with this code, it will just join. So we are safe with lifetimes, and we are passing reference to this object, and this just works. So this is how you do this when you want to pass something as a reference. All right, maybe last brain teaser about the threads. What happens here? Just to summarize and repeat maybe some things. Who sees the issue?
So maybe T1 and T3 are not joined after all the moves.
You mean about which line?
So after removing from one thread object to another, T2 would be at the end not joinable, but T1 and T3 would be might still need to join after all.
All
No,
right.
no.
Yeah.
T3 move, T1 should be joined.
Okay, exactly, right? So what we have here, we have T1, right? Then we move T1 to T2. So T1 is empty, right? So that's why I can assign a new thread to it, and there's nothing wrong with that, right?
Yes.
I create a new thread, T3, and I assign T2 to it because it's empty, so I can assign this T2 to it, right? But T1 still runs this previous thread, and I try to assign a new one, so T1 was never joined, and it has to be distracted or assigned a new value, so it will be a terminate at this point, right? Because you should join or detach first before you assign a new resource to T1 at this point. All right? If you used basically JThread here, everything would be fine because JThread will just join it in the assignment by itself, and then you will basically wait for it to finish, and then only move will happen. All right? Just use JThread as a default, right? Threads are misleading and confusing. Don't do it. If you want to spawn a bunch of threads, you basically want to create a vector of JThreads. You may reserve or not, and then place back the thread functions to the vector. All right, and then you can print some index for this thread, and this is how you create a thread pool, the easiest thread pool you may want to deal with. If you don't want to actually find out what is the good size for this vector, you can reach for hardware concurrency object in the library. JThread and thread provides that. However, this may lie. This doesn't have to actually be your hardware concurrency in the meaning of number of cores you have on your hardware, because on some platforms, the C++ library will not be able to query that information from the OS. On some virtualization or other platforms, maybe some Dockers, it will not be possible to actually find out how many cores you have for this specific Docker assigned, right? So it may return you 0. Be aware that hardware concurrency may be 0, because if you depend on it and you want to create an array of 0 elements, you may be surprised by the results of the program. All right. So what we typically do will be to run something like num threads is hardware concurrency and max 2. Right. So whichever is larger, and then you create your basically your thread pool. That's a good hint. You can also find out what the ID can be hashed, and so on. But and the last thing about threads is that you have native handle, because this is where C++ goes. You can just get ID and sleep, and that's it. You cannot do anything else on the threads. If you want to actually do some more advanced stuff, like maybe set affinities or print to some CPUs or whatever, then you actually need to deal with native handles and use native OS API to deal with that, because for now, at least in C++, we don't have means to do that in a portable way. So native handle returns you whatever underlying OS provides, and you can deal with that. And that's about JThreads. And we know about async-stream. Now we can talk about semaphores. So this is actually semaphore, not counting. Yes, counting semaphore. Okay. Semaphores is a new synchronization primitive from C++ 20, and this deals with concurrent access to a shared resource. If you think about counting semaphore, it's like a counter on a parking lot. It says you how many slots are empty, how many cars can still park there. If it will reach 0, you will have to wait for the parking lot to get emptied by some car to actually leave the parking lot so you can enter, right? So this is counting semaphore. It basically is meant to actually model a resource that can handle multiple threads at a time, right? They don't have to wait for each other to actually join. They can work independently, but only finite number of threads is allowed to enter, right? Entering a car decrements the count, leaving increments the count. When the sign shows 0, nobody enters, it's blocking, right? No parking lot ownership. None of the threads actually owns entire counting semaphore. They just use a slot assigned to them, right? So this is counting semaphore. It regulates shared access to resource that is not mutually exclusive but bounded by a maximum degree of concurrency. Unlike stud mutex, counting semaphore allows more than one concurrent access to the same resource for at least max value concurrent accessors, right? So basically you specify how many you need at least, and the hardware will, or the library will provide you the hardware that is possible for that, and you should not exceed this number at runtime if you specify this at compile time that this is your max concurrency you're going to use here. So counting semaphore has internal counter, and it will have release that may be updated with more than one, but typically you're calling this with one to just say just one car leaves the parking lot. Acquire is to acquire a slot at the parking lot. You may try acquire for, or try acquire until if needed. All right. So basically the release increments the counter, acquire decrements the counter. When 0, acquire will block until counter is incremented. Similar to condition variable weight, counting semaphore try functions can spuriously fail. The least max value is the minimum max value, not the actual max value. Max can yield basically a number larger than least max value because basically the OS may provide you the primitive that provides you more concurrency than actually you requested, which is fine. It should not just provide you less concurrency. Unlike stud mutex, counting semaphore is not tied to threads of execution. You can acquire a semaphore from one thread and release from another, and this will be fine, which is not allowed for mutexes. And all operations can be used thread safe besides the destruction. Concurrent destruction is undefined. There's also a special counting semaphore of 1. This is called binary semaphore. It may be an alias like here, but it's also allowed for the hardware to provide a dedicated hardware that provides binary semaphore of 1, which may be faster than actually the generic implementation like this. With this, you can actually also implement semaphore mutex with just lock being acquire, unlock, release. This is just a simplified mutex. Of course, probably you want to use mutex rather than that, but this is how you can model basically mutex with semaphores. However, semaphores are not used for mutual exclusion. Typically, they are used for signaling. Right? When you initialize the semaphore with the 0 blocks, the receiver, and then you can acquire until notifier signals by invoking release. Semaphores can be considered alternatives to conditional variables, often with better performance. So you may have binary semaphore, you may have signal main to thread and signal thread to main, and then you have a thread function, and the thread function basically acquires signal main to thread. So at this point it blocks because it was 0, right? So there are no slots available. Then main creates a JThread with a thread function. So this function basically thread starts and blocks here. We are writing send the signal, and we are releasing a slot on the parking lot, right? Which wakes up this thread, and we write got the signal, and then we sleep for 3 seconds. In the meantime, this main thread continues and just acquires the other block, other one, which is also 0, so it blocks again. After 3 seconds, this one wakes up, sends the signal, releases the slot, this one gets it, and you get the signal. And this is what's being printed. All right. So this is how it works, and it's much easier than conditional variables. If you ever used conditional variables, you know that you have to use mutexes, unique locks, conditional variables, set proper states of mutexes before you call specific functions of conditional variables. That's a lot of headache to actually make it work. If you want to see this headache, come to the workshop, because we are going to practice conditional variable as well, and then you're going to find out how those new abstractions in C++20 are much better and easier to work with. Okay. As expected, we are nearly out of time. So we are not going to actually break out in the breakout rooms. On the workshops, we are going to do that. But now you have an exercise and a link. And this link is here. I will maybe copy the link and put it to the other Snow chat. All right, but you have on the slides and you can retype it later on. So you will be able to actually play with this exercise by yourself and solve this solution, right? And those are the kind of exercises we are doing on our workshops. I know that I spoke quite fast and I progressed with material quite fast because I wanted to fit with some meaningful, minimal example that actually has a thread-safe printing, JFrets, and one synchronization primitive in 45 minutes, which was a lot. Sorry if this was too fast for you. On the workshop, we are going to do this slower and have more time for discussion, right? But I wanted to provide you all of the knowledge to actually be able to do this one simple exercise in the end. And also, as expected, we don't have much time because I have to start another session like in 2 minutes. This is the exercise for you. You basically have rental car pipeline, and you want to actually have threads representing a car, and each car will be washed and parked. For some, basically, it will be an operation that takes some time. All right? And you want to implement proper number of permits for each resource. 1 permit for car wash, 3 permits for parking lots, and you want to make this code concurrent. So we have to create 5 threads. Each car should first be washed, then parked on the parking lot, and you want to provide thread-safe logging. So all of the things that we discussed so far during this really short and, sorry, too fast maybe, teaser. All right? The solution will be to use concurrent resource, basically to modify concurrent resource to have here async streams. You may provide some printing, emit the print here, acquire the resource, call the function, release the resource, and then everything works if you create a pool of 5 threads. Create pool of 5 threads, reserve, and place back car wash, parking lot, and this just works. You can try it out by yourself. You get the link, but please don't try to look into the solution before you actually do it by yourself. Try doing this by yourself, and you will find out that it's not that easy as it seems on this slide. Because seeing code is easy. Writing this code by yourself, it's harder. So that's why I typically even don't provide solutions to my students. I just provide them links and I say, just do it again, just do it again, just do it again. Don't look into the solutions because you are not going to learn. Watching slides, watching code does not make your fingers learn how to type code. And this is basically how I think and how I reason about the workshops, right? If you like this approach, of course, attend the workshops after the conference or hire me to your company and take one of the workshops, for example, this one, the actually full 4-day class about concurrent and asynchronous programming with those primitives that we're going to learn, coroutines, and senders receivers. Or advanced model C++ when you're going to learn about error values and many other things. It's probably my most popular and probably one of the best classes I have because it teaches you how the language works. It's a 5-day class. Or I have classes about design, C++20, or CMake and Conan. You can find my offer at Trinity EU. And that's basically it. We are out of time. I'm going to take some questions after the second part. So if you want to ask questions, please stay. All right. And I will just switch soon to the next part of our teasers.